Hello everyone, my name is Roee and I'm a PhD candidate at the Technion. Today I will present our paper titled Cross-Domain Schema Matching using Deep Similarity Matrix Adjustment and Evaluation. The work was conducted jointly with my advisor Avigdor and Haggai Roitman from eBay Research. In this work, we tackled the problem of schema matching. Schema matching is a key component in data integration with the main incentive of providing correspondences between data elements, for example, database attributes. By way of motivation, consider the following word cloud with the most common column headers as extracted from thousands of web tables. As we can see, frequent headers lack semantics and use extremely general terms. For example, description here, one of the most frequent column headers, can address a customer, a store, a product, and so on. To illustrate our schema matching model, we shall use the following example, representing two purchase order schemata. The basic procedure of schema matching applies matchers to generate similarity matrices. In our example, this is how an attribute name matcher called term would complete a similarity matrix. For example, the similarity level between the two city attributes is 1, while the similarity level between order date and PO time is only 0.11. In this work, we focus on two tasks applied over similarity matrices. The first is evaluation, aiming to assess a matrix ability to identify correct correspondences. Common examples include precision and recall. Usually, aiming to evaluate a matrix in the absence of a reference match, evaluators use human intuition. In this work, we defined monotonic evaluators as evaluators that behave like known evaluation functions such as precision, recall, and F1 measure. The second task is adjustment. A similarity matrix adjustment transforms a similarity matrix into a potentially better one. Adjustment is also known as second-line matcher in schema matching literature and usually uses human-guided rules such as one-to-one matching and bound setting. We define a consistent adjustment as an adjustment that assures quality improvements with respect to some evaluation measure, as we can see. Here are two examples of similarity matrix adjusters. The top one simply selects the entries with values above 0.1. In the bottom example, a maximum weight betitled graph matching is used to determine a one-to-one matching. The motivation for our proposed adjust and evaluate algorithm is to capture relationships among matrix elements using deep neural networks that are not captured using human-designed rules and heuristics. To do so, we designed a multitask neural network that both adjusts and evaluates similarity matrices, as the similarity matrices that we use are generated by state-of-the-art heuristic schema matchers. One important thing to note here is that generating a large enough training set in the setting of schema matching is far from trivial, and actually was one of the main obstacles in applying deep learning for schema matching prior to our work. The main insight here in terms of generating a sufficiently large data set is that similarity matrices can serve as training example. This way, we can generate dozens of similarity matrices for a given schema pair. In addition, in our work, we suggest a novel augmentation technique for similarity matrices to further extend the training set of similarity matrices. Please refer to our paper for additional details. The input for our algorithm is a similarity matrix, and its initial step uses a trained neural evaluator to evaluate the given matrix. Then, we adjust the similarity matrix using our pre-trained neural adjuster and check whether the adjusted matrix is better using our pre-trained evaluator. We repeat these two steps until no improvement is obtained anymore. And then finally, we return the last matrix as the output for our algorithm. In the paper, we provide conditions under which convergence and dominance can be guaranteed for our algorithm. In our evaluation, we analyzed three main properties. The first is to show that the proposed algorithm can generalize beyond a single domain. The second is to show that the algorithm performs well on challenging real-world benchmarks of schema matching. Finally, we show that our algorithm also performs well on the related problem of ontology alignment. Here we can see a sketch of our algorithm over a concrete real-world similarity matrix. Due to time restrictions, I chose to show only the cross-domain ability of our algorithm. More analysis is given in the paper, including an analysis of the different components of our algorithm. As we can see, the algorithm beats the baselines over all the domains. Specifically, we can see that the algorithm performance varies across the domains in comparison to the baseline, whose performance is fairly stable. This may suggest that while some domains, such as forums and job posting, reach impressive cross-domain performance, others, such as news and aviation, are harder to match, and aiming to generalize from different domains to these specific domains is more challenging than others. Similar trends exist for precision and recall for the cross-domain evaluation, and as I referred to earlier, all the results are given in the paper. Thank you very much for the attention, and I am available here in this email address and this website, as well as here for the Q&A session after the video. Thank you very much, and have a lovely day.